This is Sleepy Space, a slow space story to help you fall asleep. Right now, as you listen to these words, you are moving. Not in the small ways you might notice, not the rise and fall of your breathing or the subtle shift of your body. You are moving through space at speeds so great that if you could perceive them directly, the world around you would blur into streaks of light and color. The strange part is that you feel perfectly still. You are standing on the surface of a rotating planet. Earth spins once every 24 hours, carrying you eastward whether you notice it or not. At the equator, that motion reaches roughly 1,000 miles per hour, faster than the speed of sound, faster than any commercial aircraft. And yet, there is no wind in your face, no vibration beneath your feet, just stillness. That sense of stillness is an illusion, because Earth itself is moving. Our planet orbits the Sun, tracing a vast elliptical path through space at nearly 67,000 miles per hour. In the time it takes you to read a single paragraph, you have already traveled hundreds of miles around our star. By the time you reach the end of this chapter, you will have traveled thousands more. And the Sun does not stand still either. Our entire solar system is moving through the Milky Way galaxy, orbiting its center in a slow, sweeping arc that takes hundreds of millions of years to complete. This motion carries us at roughly 500,000 miles per hour. 500,000 miles per hour, a speed so extreme it defies human intuition. Still, you feel nothing. The Milky Way itself is not at rest. It is moving through space alongside its neighbors, drawn by gravity toward the Andromeda Galaxy. Together, they drift through the local group of galaxies, pulled by vast gravitational flows that stretch across millions of light years. Motion upon motion, rotation, revolution, orbit, drift, all of it happening at once, all of it invisible to your senses. You experience stillness only because everything around you is moving together. The air moves with the earth, the ground moves with the sun moves with the galaxy. When motion is shared, it disappears from perception. This reveals something fundamental about the universe. Nothing is still. Nothing has ever been still. True rest, absolute rest, does not exist. Stillness is not a physical state. It is a relative one. When you say you are sitting still, what you really mean is that you are still relative to the chair beneath you, relative to the room around you, relative to the surface of the planet. But the planet is not still. The planet cannot be still. Nothing in the cosmos is allowed that luxury. Motion is not an exception. It is the rule. At the smaller scales, particles vibrate and fluctuate even at temperatures approaching absolute zero. Electrons do not sit quietly around atomic nuclei. They exist as clouds of probability, always in motion. Atoms combine into molecules that twist, collide, and rearrange themselves endlessly. At larger scales, planets orbit stars, stars orbit galactic centers, galaxies collide, merge, and tear one another apart. Galaxy clusters drift through space, bound together by gravity, stretching and evolving across billions of years. Motion is everywhere because it must be. Without motion, there would be no chemistry. Molecules could not collide, reactions could not occur. Without motion, there would be no heat, because temperature is simply the movement of atoms. Without motion, there would be no light, because light itself is energy in motion. rippling through space. Without motion, life would be impossible. Even time may depend on it. Some physicists argue that time is nothing more than change, and change is motion. If nothing moved, if nothing evolved or transformed, time itself might lose meaning. The universe would be frozen, not alive, not dead, but static in a way that makes before and after irrelevant. But our universe is not frozen. It spins, it flows, it expands. And within that vast moving cosmos, you exist as motion too. The atoms in your body are not permanent residents. Over the course of years, they are exchanged with the environment, breathed out, eaten, absorbed, replaced. What persists is not the matter itself, but the pattern, the arrangement, the ongoing process. You are not a thing, you are an event, a temporary pattern of motion held together by forces, existing briefly in a universe that never stops moving. So when you sit quietly and feel at rest, remember what is actually happening. You are rotating with the Earth. You are orbiting the Sun. You are flying through the galaxy at speeds that would terrify you if you could perceive them. You are part of a universe that has never known stillness, and perhaps cannot know it. To understand why motion is so fundamental, why nothing in the universe can ever truly stop, we need to go back to the very beginning, back to a universe born already in motion. 13.8 billion years ago, the universe began. Not with an explosion in the way we typically imagine explosions, not as a blast of matter and energy erupting into empty space. The Big Bang was something stranger, something more fundamental. It was the beginning of space itself, the beginning of time itself. And from the very first moment, it was a state of expansion, a state of motion. Before the Big Bang, there was no before. Time did not exist. Space did not exist. There was no stage on which events could unfold, no clock by which to measure duration. And then, in an instant that cannot be fully described by our physics, everything came into being. Space began to expand. Time began to flow. And within that expanding space, energy condensed into the first particles of matter. Everything emerged already moving. The expansion of space carried matter with it, pulling regions of the early universe apart. This was not movement through space in the conventional sense. It was the expansion of space itself, stretching the fabric of reality, creating more distance between points with each passing moment. And it happened fast. Faster than anything that would ever happen again. In the first fraction of a second, a period of time so brief it is almost meaningless to describe, the universe underwent what physicists call inflation. Space expanded exponentially, doubling in size again and again in intervals smaller than a trillionth of a second. A region smaller than an atom swelled to something larger than a galaxy in less time than light takes to cross a single proton. The universe didn't just begin in motion, it began in the most violent, rapid motion imaginable. When inflation ended, the expansion continued, but at a more sedate pace. Space kept stretching, matter kept spreading. The early universe was unimaginably hot, a seething plasma of particles colliding and separating and colliding again. As the universe expanded, it cooled. Particles slowed. Forces began to take their modern forms. But the expansion never stopped. For billions of years, this expansion continued unabated. Galaxies formed from clouds of gas drawn together by gravity. Stars ignited, planets coalesced. But through it all, the underlying expansion persisted. Every region of space on the largest scales continued to move away from every other region. The universe was not static. It had never been static. It was born moving, and it has been moving ever since. We know this because we can see it. In the early 20th century, astronomers began to notice something strange about distant galaxies. When they analyzed the light from these galaxies, they found that it was red-shifted. The wavelengths of light were stretched, shifted toward the red end of the spectrum. This redshift was a sign of motion. The galaxies were moving away from us. Edwin Hubble confirmed this pattern. He measured distances to galaxies and compared them to their velocities. What he found was remarkable. The farther away a galaxy was, the faster it was receding. This was not because we were at the center of some cosmic explosion. It was because space itself was expanding. Every point in the universe was moving away from every other point, carried by the stretching of space-time. Imagine dots painted on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. None of them are special. None of them are at the center. The surface itself is expanding, and that expansion carries the dots with it. This is what happens in our universe, but in 3 dimensions instead of 2. Space expands and galaxies move apart, not because they are traveling through space, but because space is growing between them. We can measure this expansion. We can calculate how fast distant galaxies are receding based on their distance from us. The expansion rate, known as the Hubble constant, tells us how quickly the universe is growing. For every million light-years of distance, space expands by a certain amount each second. The numbers are precise, though they require careful observation and sophisticated instruments to determine. This expansion has profound implications. It means the universe had a beginning. If we run the expansion backward in time, tracing the paths of galaxies in reverse, they converge. 13.8 billion years ago, they were all in the same place. Or rather, all places were the same place. Space itself was compressed into an infinitesimally small point. The Big Bang was not an explosion into empty space. It was the expansion of space from a singularity, a point of infinite density where our current laws of physics break down. The Big Bang did not just create matter and energy. It created motion as a fundamental property of the universe. Everything that exists emerged from that initial expansion, carrying the momentum of creation itself. The motion we see today at the largest scales is the echo of that primordial event. Galaxies moving apart, space stretching, the universe expanding. In the early moments after the Big Bang, particles raced through space at tremendous speeds, colliding and interacting in the dense, hot plasma. As the universe expanded and cooled, these particles began to clump together under the influence of gravity. Small variations in density, tiny quantum fluctuations inflated to cosmic scales during inflation, became the seeds of structure. Gas clouds formed, they collapsed, and in collapsing, they began to spin. The expansion of the universe explains why galaxies move apart from each other. It explains the large-scale motion of cosmic structures, the flow of matter across billions of light-years. But it does not explain everything. It does not explain why galaxies spin, why stars orbit galactic centers, why planets orbit stars, why you are rotating right now on Earth's surface, carried by a spin that has persisted for billions of years. For that, we need to understand something more personal, more local. We need to understand a principle that governs motion at every scale, from the smallest atoms to the largest galaxies. We need to understand angular momentum. Angular momentum is spin that persists. It is rotation that refuses to stop. Once something begins to spin, it keeps spinning unless something else acts on it to slow it down or speed it up. This is not just a tendency. It is a law of physics, as fundamental as the conservation of energy or the constancy of the speed of light. Angular momentum cannot be created from nothing. It cannot be destroyed. It can only be transferred from one object to another. Think of an ice skater spinning on the ice. Arms extended, rotating at a moderate speed. Then the skater pulls their arms inward, tight against their body. Suddenly, they spin faster, much faster. The rotation accelerates dramatically, even though no external force was applied. This is conservation of angular momentum in action. The skater's total angular momentum must remain constant. When they reduce their radius by pulling in their arms, their rotation speed must increase to compensate. This same principle applies at every scale in the universe. When a cloud of gas and dust in space begins to collapse under its own gravity, any rotation it has, no matter how slight, amplifies. The cloud contracts. Its radius decreases. And just like the ice skater, its rotation speed increases. What started as a barely perceptible drift becomes a powerful spin. 4.6 billion years ago, a cloud of gas and dust floated in the Milky Way galaxy. It was vast, stretching across light years of space, and it was rotating ever so slowly. Perhaps it had been nudged by the shock wave from a nearby supernova. Perhaps it had inherited some residual spin from the turbulent motions of the galaxy itself. The exact cause does not matter. What matters is that it had angular momentum, and that angular momentum could not disappear. Gravity began to pull the cloud inward. Particles of gas and dust fell toward the center, drawn by the collective mass of the cloud. As the cloud contracted, it spun faster. The rotation that had been almost imperceptible became significant. The cloud began to flatten. Material moving perpendicular to the axis of rotation fell inward easily, but material moving parallel to the axis of rotation resisted collapse. It wanted to keep spinning outward, held aloft by centrifugal effects. The result was a disk, a flat, rotating disk of gas and dust, spinning around a dense central core that would become the Sun. This is why our solar system looks the way it does, why the planets all orbit in roughly the same plane, why they all travel in the same direction around the Sun. They formed from a spinning disk, and they inherited the angular momentum of that disk. Each planet, as it coalesced from the material in the disk, carried its own share of the original rotation. Earth spins because the fragments that collided to form it were already moving, already rotating as they orbited the young Sun. Those collisions added their angular momentum together. Some impacts sped up Earth's rotation, others slowed it down. The final spin we see today is the net result of billions of collisions, averaged out over millions of years of planet formation. The Moon's orbit around Earth is angular momentum as well. When a Mars-sized object collided with the early Earth, ejecting debris that would eventually coalesce into the Moon, that debris was already moving. It had angular momentum inherited from the collision, from the orbital motion of the impactor. The Moon formed from that spinning ring of debris, and it has orbited Earth ever since, carrying the angular momentum of that ancient catastrophe. This principle extends beyond our solar system. Every star system forms from a collapsing gas cloud. Everyone goes through the same process. Collapse, spin up, flatten into a disk. The details vary, but the physics remains the same. Angular momentum is conserved. Rotation persists. Galaxies spin for the same reason. When the first galaxies formed in the early universe, they coalesced from vast clouds of gas that had been seeded by tiny density fluctuations in the Big Bang. These clouds had rotation inherited from the turbulent motions of the expanding universe, from the gravitational interactions of neighboring structures. As the gas clouds collapsed under their own gravity, they spun faster. They flattened into disks. And the stars that formed within those disks inherited the rotation, orbiting the galactic center in grand, sweeping paths that take hundreds of millions of years to complete. The Milky Way contains hundreds of billions of stars. Each one orbits the galactic center. Each one carries angular momentum. Our Sun takes roughly 230 million years to complete one orbit. Other stars move faster or slower depending on their distance from the center, but all of them orbit in the same general direction, like horses on a cosmic carousel, locked into paths defined by angular momentum and gravity. Even elliptical galaxies, which lack the flat disk structure of spirals, have angular momentum. Their stars orbit in more chaotic, three-dimensional patterns, but they still orbit. They still move. The angular momentum is distributed differently, less organized, but it is there. It persists. At the smaller scales, angular momentum governs the behavior of atoms. Electrons do not orbit the nucleus in the way planets orbit the sun. Quantum mechanics forbids such simple trajectories, but electrons do have angular momentum. They exist in orbitals, regions of space defined by their energy and angular momentum. These orbitals have shapes and orientations determined by quantum numbers, abstract values that encode how much spin and rotation the electron carries. Even fundamental particles have angular momentum. Protons, neutrons, electrons all have a property called spin. This is not spin in the classical sense. Particles do not literally rotate like tiny tops, but they have angular momentum nonetheless, an intrinsic property that behaves mathematically like rotation. This quantum spin is conserved in particle interactions. It cannot be created or destroyed, only transferred or combined. Angular momentum is everywhere. It is woven into the structure of the cosmos. It explains why planets orbit, why galaxies rotate, why electrons occupy the orbitals they do. It is a consequence of symmetry, of the fact that the laws of physics do not depend on direction. Rotation in any direction is as valid as rotation in any other direction, and this symmetry leads directly to the conservation of angular momentum. But angular momentum alone does not explain all motion. It tells us why spinning things keep spinning. It tells us why orbits persist, but it does not tell us why objects orbit in the first place. It does not explain the force that holds planets to stars, stars to galaxies, galaxies to each other. For that, we need another force, one that reaches across empty space, pulling everything toward everything else. Gravity is the force that shapes the cosmos. It reaches across empty space, invisible and relentless, pulling every piece of matter toward every other piece of matter. It holds planets in orbit around stars. It binds stars into galaxies. It draws galaxies into clusters. And it does all of this without ever touching anything, without any physical connection between the objects it influences. Gravity is weak compared to other fundamental forces. The electromagnetic force that holds atoms together is vastly stronger. Yet gravity dominates at large scales because it is always attractive, always pulling, never pushing. And because it acts on mass, and mass accumulates. The more matter you gather in one place, the stronger gravity becomes. But if gravity only pulls inward, if it only attracts, why doesn't everything collapse together? Why doesn't the moon crash into Earth? Why doesn't Earth spiral into the sun? Why do galaxies maintain their structure instead of collapsing into single points? The answer is motion. Motion saves us from collapse. Objects moving fast enough can fall towards something without ever reaching it. They can fall continuously, perpetually, tracing a curved path through space that brings them no closer to their destination. This is what an orbit is. A state of constant falling that never ends in collision. Isaac Newton understood this centuries ago. He imagined a cannon on top of a tall mountain, firing a cannonball horizontally. If the cannonball is fired slowly, it arcs downward and hits the ground some distance away. If it is fired faster, it travels farther before landing. Faster still, and it travels even farther. But at a certain speed, something remarkable happens. The cannonball travels so far horizontally that the curve of its fall matches the curve of Earth's surface. It falls toward the ground, but the ground curves away beneath it at the same rate. The cannonball never lands, it orbits. This is orbital velocity, the precise speed needed to balance gravity's inward pull with the outward motion of the object. Too slow, and gravity wins. The object spirals inward, too fast, and the object escapes, flying off into space. But at just the right speed, the object maintains a stable orbit, falling forever without ever reaching the surface. The moon orbits Earth at roughly 2,000 miles per hour. That is its orbital velocity at its current distance. It is constantly falling toward Earth, pulled by gravity. But it is also moving sideways, tangent to its orbital path. And this sideways motion is fast enough that it keeps missing Earth. It falls around us instead of into us, month after month, year after year. For billions of years, the moon has traced this same path, held in a delicate balance between gravity and motion. Earth orbits the sun in the same way. Our orbital velocity is approximately 67,000 miles per hour. At this speed, we fall toward the sun continuously, but we also move sideways fast enough that we never get closer. We trace an elliptical path through space, one that brings us slightly closer to the sun during winter in the northern hemisphere and slightly farther during summer. But always we maintain the orbit. Always we fall without landing. If Earth moves slower, even by a small amount, our orbit would decay. We would spiral inward, drawn closer to the sun with each pass. Temperatures would rise, oceans would boil, life would end. If Earth moved faster, we would drift outward. Our orbit would widen, temperatures would drop, the planet would freeze. The balance is precise, maintained by the speed we inherited from the spinning disk that formed the solar system. Every planet orbits the sun at its own velocity, determined by its distance from the sun and the strength of the sun's gravity at that distance. Mercury, close to the Sun, travels fastest, whipping around its orbit in just 88 Earth days. Neptune, far from the Sun, moves slowly, taking more than 160 Earth years to complete a single orbit. But all of them maintain the balance. All of them fall continuously without ever falling in. Stars orbit the centers of their galaxies in the same way. Our Sun orbits the Milky Way's galactic center at roughly 500,000 miles per hour. This seems fast, and it is. But at our distance from the center, roughly 26,000 light-years, this speed is necessary to maintain orbit. The combined gravity of hundreds of billions of stars, along with the dark matter that pervades the galaxy, pulls inward. Our sideways motion keeps us from spiraling in. Binary star systems demonstrate this principle beautifully. Two stars, locked in mutual orbit, each falling toward the other but never colliding. They circle a common center of mass, their orbital velocities determined by their masses and the distance between them. Some binary stars are so close they complete an orbit in hours. Others take centuries, but in every case the motion is what keeps them apart. Without it, gravity would pull them together in a catastrophic merger. Even black holes, objects with gravity so strong that nothing can escape from within their event horizons, can be orbited. If you approach a black hole at the right speed and angle, you can enter a stable orbit circling it just as Earth circles the Sun. You would fall toward the black hole continuously, but your sideways motion would keep you at a constant distance. At least, it would until tidal forces or radiation from the accretion disk destroyed you. But the orbit itself would be stable, a testament to the universal balance between gravity and motion. Gravity creates motion by pulling objects together, but paradoxically, motion prevents gravity from fully succeeding. Objects fall, but they fall sideways, tracing curves through space. And as long as they maintain their speed, they can fall forever without ever reaching their destination. This explains the large-scale motions we observe, the orbits of planets, the rotation of galaxies, the dance of binary stars. Gravity provides the inward pull, and angular momentum provides the sideways motion. Together, they create the stable structures we see throughout the cosmos. But gravity and angular momentum govern motion at scales where objects are large, where classical physics applies. Motion exists at scales far smaller, in realms where gravity barely matters at all. In the world of atoms and molecules, where different forces dominate and different rules apply, the chair beneath you feels solid. The floor supporting your feet seems still. The air around you appears calm and motionless. But this is an illusion. At the scale of atoms, everything is in constant, frenetic motion. The solid objects you perceive are actually swarms of particles vibrating, jiggling, bouncing against each other billions of times per second. Temperature is motion. When you feel heat, you are sensing the kinetic energy of atoms. The faster atoms move, the hotter something feels. The slower they move, the colder it becomes. A hot cup of coffee contains water molecules racing around at high speeds, colliding with each other and with the walls of the cup. As the coffee cools, those molecules slow down. The motion decreases, the temperature drops, but the motion never stops entirely. Even ice contains atoms in motion. The water molecules in ice are locked into a crystalline structure held in place by electromagnetic forces. But they still vibrate. They oscillate around their equilibrium positions, never truly still. This vibration is what temperature measures. Even in a frozen solid, there is a theoretical temperature at which all atomic motion would cease. Scientists call it absolute zero. On the Celsius scale, it occurs at negative 273.15 degrees. On the Kelvin scale, it is zero. At this temperature, atoms would stop vibrating. Molecules would stop rotating. All thermal motion would halt. But absolute zero is impossible to reach. You can get close. You can cool matter to within a fraction of a degree of absolute zero using sophisticated techniques. But you cannot reach zero itself. Quantum mechanics forbids it. Even at the lowest possible temperatures, atoms retain what physicists call zero-point energy. They cannot be perfectly still. The uncertainty principle demands that they keep moving, at least a little. Werner Heisenberg discovered this principle in the early 20th century. It states that you cannot know both the exact position and exact momentum of a particle simultaneously. The more precisely you know where something is, the less precisely you can know how fast it is moving. And if a particle were perfectly still, sitting at a single point in space, you would know both its position and momentum exactly. Position would be precise. Momentum would be zero. This violates the uncertainty principle. Nature does not allow it. So even at absolute zero, particles must have some motion, some irreducible jitter that prevents them from being perfectly localized. This is not just a limitation of measurement, it is a fundamental property of reality. Particles cannot be still because stillness would require more information than the universe permits. Inside atoms, motion is even more fundamental. Electrons exist in clouds around the nucleus, probability distributions that describe where the electron might be found if you were to look for it. These clouds are not static. The electron is not sitting somewhere within the cloud, waiting. It is the cloud. It exists in a state of quantum superposition, spread out across space, with no definite position until something interacts with it and forces it to choose. But even this strange quantum state involves motion. Electrons have kinetic energy. They have angular momentum. They move, though not in the way we typically think of movement. They are not little balls orbiting a central nucleus like planets around a star. They are waves of probability, oscillating, interfering with themselves, creating the patterns we observe when we measure their properties. Inside the nucleus, motion becomes even more extreme. Protons and neutrons are packed together in a space so small, it defies imagination. A nucleus is roughly 100,000 times smaller than the atom as a whole. And within that tiny space, protons and neutrons are constantly moving, constantly interacting through the strong nuclear force that holds them together. Protons and neutrons are not fundamental particles. They are made of quarks, bound together by gluons, and quarks move at speeds approaching the speed of light. Inside a single proton, 3 quarks zip around each other, held together by gluons that themselves carry energy and momentum. The motion is so fast, so energetic, that most of the mass of a proton comes not from the quarks themselves, but from the kinetic energy of their motion. You are made, in large part, not of matter, but of moving energy. Zoom out from the nucleus back to the scale of molecules, and motion manifests in different ways. Molecules rotate, they vibrate, they translate through space, bouncing off each other in a chaotic dance. In a gas, molecules are far apart, moving freely at high speeds. In a liquid, they are closer together, still mobile but constrained by intermolecular forces. In a solid, they are locked into position, but they still vibrate. This molecular motion is what Robert Brown observed in the early 19th century when he looked at pollen grains suspended in water through a microscope. The grains jiggled and moved erratically, dancing across his field of view. Brown initially thought the pollen might be alive, driven by some biological force. But he soon realized that even inorganic particles exhibited the same motion. The movement was not coming from the particles themselves. It was coming from the water molecules colliding with them. This Brownian motion is visible proof of atomic movement. The water molecules, far too small to see individually, bombard the pollen grain from all sides. Most of the time, the collisions balance out, and the grain stays relatively still. But occasionally, by chance, more molecules hit from one side than the other. The grain shifts, it moves. And because the collisions are random, the motion is erratic, unpredictable. Brownian motion confirms what theory predicts. Atoms and molecules are in constant motion. They do not need to be pushed or pulled by external forces. The motion is intrinsic, built into the fabric of matter itself. It arises from temperature, from the kinetic energy distributed among particles. And as long as temperature exists, as long as we remain above absolute zero, this motion will continue. Solid objects are not solid in the way we intuitively imagine. The desk in front of you is mostly empty space. Atoms are mostly empty space. The nucleus occupies only a tiny fraction of the atom's volume. The rest is the electron cloud, regions of space where electrons might be found, but are not in any classical sense present. And even the parts that seem substantial, the nucleus and the electrons, are in constant motion. When you press your hand against a table, you are not touching the table in a direct, physical sense. The atoms in your hand and the atoms in the table never make contact. What you feel is the electromagnetic force between them, electrons in your skin repelling electrons in the table surface. These electrons are moving. They are vibrating, oscillating, existing in quantum states of motion. And that motion, translated through layers of atoms and molecules, is what your nerves interpret as solidity. Motion at the atomic scale is not an afterthought, not a secondary phenomenon. It is central to the nature of matter. Without it, chemistry would not work. Molecules would not react. Bonds would not form or break. Life, which depends on countless chemical reactions happening in precise sequences, would be impossible. From quantum particles to planets, from atoms to galaxies, motion is everywhere. But perhaps the most profound motion is the one we cannot see at all. The one that carries us all forward inexorably, second by second. Albert Einstein changed how we understand motion. In the early 20th century, he proposed something radical. Space and time are not separate. They are not independent dimensions through which objects move. They are unified, woven together into a single four-dimensional fabric called space-time. And everything that exists moves through this fabric, not just through space, but through time as well. This is difficult to grasp. We experience space and time as fundamentally different. We can move freely through space, forward, backward, left, right, up, down, but we cannot move freely through time. We are carried forward 1 second per second with no apparent choice in the matter. Yet Einstein showed that this distinction is an illusion. Space and time are connected. How you move through one affects how you move through the other. Here is the revelation. Everything in the universe moves through space-time at the same speed. Always. That speed is the speed of light, roughly 300 million meters per second. This is not just the speed at which light travels through space. It is the speed at which everything moves through space-time itself. When you sit still, when you think you are not moving through space, you are moving through time at maximum speed. All of your motion through space-time is directed along the time dimension. 1 second of your time passes for every second of universal time. You age at the normal rate. Clocks around you tick at the normal rate. Everything proceeds as expected. But when you move through space, something changes. Some of your motion through space-time is now directed along a spatial dimension. You are moving through space, which means you must be moving through time more slowly. Your total speed through space-time remains constant, always the speed of light. But now that speed is divided between motion through space and motion through time. This is time dilation. The faster you move through space, the slower you move through time. At everyday speeds, the effect is negligible, imperceptible. But at speeds approaching the speed of light, the effect becomes dramatic. If you could travel at 90% the speed of light, time for you would pass at roughly half the rate it passes for someone at rest. You would age more slowly. Your clocks would tick more slowly. Not because something is wrong with you or your clocks, but because you are moving through space-time in a different way. At the speed of light itself, all motion through space-time would be directed through space. None would be directed through time. This is why light does not experience time. A photon emitted from a distant star travels billions of light years to reach us. From our perspective, that journey takes billions of years. But from the photon's perspective, if we can speak of such a thing, the journey is instantaneous. The photon is emitted and absorbed in the same moment. No time passes for it. It moves through space at light speed, which means it does not move through time at all. This also explains why nothing with mass can reach the speed of light. To do so would require moving only through space, not through time. But matter exists in time. It ages, it changes, it evolves. To stop moving through time would be to stop existing in the way we understand existence. The universe forbids this. As you accelerate through space, approaching the speed of light, it becomes harder and harder to go faster. Your mass, from the perspective of an outside observer, increases. The energy required to accelerate you further grows without bound. You can never quite reach light speed because doing so would require infinite energy. Gravity complicates this picture. Einstein realized that gravity is not a force in the conventional sense. It is a curvature of space-time. Massive objects like stars and planets warp the fabric of space-time around them, creating curves and valleys in the four-dimensional landscape. When you fall toward Earth, you are not being pulled by a force. You are following the straightest possible path through curved space-time. This curvature affects motion through time as well as motion through space. Near a massive object, space-time is warped. Time runs more slowly. If you were to stand near the event horizon of a black hole, time for you would pass at a drastically reduced rate compared to someone far from the black hole. hours for you might correspond to years for them. This is not an illusion. It is a real, measurable effect. Time itself moves differently in different regions of space-time, depending on the curvature. Satellites orbiting Earth experience this. They are moving quickly through space, which causes their clocks to run slower due to velocity time dilation. But they are also farther from Earth's gravitational field, where space-time is less curved, which causes their clocks to run faster due to gravitational time dilation. The two effects partially cancel, but not completely. Engineers must account for these relativistic effects when designing GPS systems. Without these corrections, the system would fail, accumulating errors of several kilometers per day. You are moving through space-time right now. You cannot stop. Even if you could eliminate all motion through space, even if you could stand perfectly still relative to every reference frame in the universe, you would still move through time. Space-time does not permit stillness. Existence itself is motion. The past is not a place you have left behind. The future is not a place you are heading toward. They are directions in space-time, as real as north and south. You move through space-time along a path called your world line. This world line traces your entire history, from birth to death, as a continuous curve through four-dimensional space. Every moment of your life exists somewhere along that curve. Every decision you make, every breath you take defines the shape of your world line. Other objects have world lines too. A rock sitting on the ground has a world line that moves only through time, not through space. A photon has a world line that moves through space at the maximum rate, with no motion through time. A planet orbiting a star has a world line that spirals through space-time, looping in space while progressing steadily through time. These world lines can intersect. When they do, we call it an event. Two particles colliding, a person picking up an object, a star exploding. Events are points in space-time where world lines meet, and the structure of space-time determines which world lines can intersect, which events are possible, which futures are accessible from a given present. Space-time is not a passive stage on which motion occurs. It is an active participant. It curves in response to matter and energy, and that curvature dictates how objects move. Matter tells space-time how to curve. Space-time tells matter how to move. This feedback loop is the essence of general relativity, Einstein's theory of gravity. You cannot escape motion through space-time. It is as fundamental to your existence as the atoms that make up your body. You are not moving through time. You are time. Your progression from moment to moment is what time means for you. And that progression is motion, as real and unavoidable as any journey through space. But there is one final motion we have not yet addressed, one that might be the strangest of all. The universe is expanding. We have known this for nearly a century. Galaxies move apart from each other, carried by the stretching of space itself. This expansion is the echo of the Big Bang, the initial motion from which all other motions descend. But in 1998, astronomers discovered something unexpected, something that changed our understanding of the cosmos. The expansion is accelerating. Two teams of researchers were studying distant supernovae, brilliant stellar explosions that can be seen across billions of light years. These supernovae serve as cosmic distance markers. Their brightness tells us how far away they are. Their redshift tells us how fast they are receding from us. By comparing these two measurements, astronomers can track the expansion rate of the universe at different points in its history. What they found defied expectations. Distant supernovae were fainter than they should have been. This meant they were farther away than predicted. The universe had expanded more than it should have if the expansion rate were constant or slowing down. Something was causing the expansion to accelerate. The universe was not just growing, it was growing faster over time. This discovery earned a Nobel Prize. It also posed a profound mystery. What could cause the expansion to accelerate? Gravity pulls galaxies together. It should slow the expansion, not speed it up. Yet the data was clear. The universe was accelerating. Physicists proposed an explanation. There must be something filling space, something with negative pressure that pushes outward instead of pulling inward. They called it dark energy. Not because it is dark in the sense of blocking light, but because we do not know what it is. It is invisible, undetectable except through its gravitational effects, and it makes up roughly 68% of the total energy content of the universe. Dark energy does not clump like matter. It does not form galaxies or stars or planets. It is spread uniformly throughout space, a constant background energy that permeates everything. As the universe expands, more space is created and more dark energy comes into existence. This increasing dark energy drives the acceleration, pushing galaxies apart at ever-increasing rates. The implications are staggering. Galaxies that we can see today will eventually accelerate beyond our reach. In tens of billions of years, they will recede so quickly that their light will never reach us. They will cross what is called the cosmic event horizon, a boundary beyond which information cannot travel. From our perspective, they will disappear. The observable universe will shrink. Eventually, only our local group of galaxies will remain visible. The Milky Way, Andromeda, and a few dozen smaller galaxies bound together by gravity. Everything else will have accelerated away, vanished beyond the horizon. Future astronomers, if they exist, will see a universe much emptier than the one we observe today. They will have no direct evidence of the Big Bang, no distant galaxies to measure, no cosmic microwave background stretched into invisibility. They will live in an island universe, isolated and alone. But even within that island, motion will continue. Galaxies will still rotate. Stars will still orbit galactic centers. Planets will still circle stars. The local motions, the ones governed by gravity and angular momentum, will persist. Dark energy affects only the largest scales. Within gravitationally bound structures, expansion has no effect. In the far future, trillions of years from now, stars will stop forming. The gas needed to create new stars will be exhausted. Existing stars will burn out, one by one. White dwarfs will cool. Neutron stars will radiate away their heat. Black holes will remain, but even they will eventually evaporate through Hawking radiation, a quantum process that allows black holes to lose mass over unimaginably long timescales. Eventually, the universe will reach a state of maximum entropy. No gradients, no differences in temperature or density, no energy available to do work. This is sometimes called the heat death of the universe. A cold, dark, empty cosmos where nothing changes, where motion in any meaningful sense might finally cease. but that is trillions upon trillions of years away, an incomprehensible span of time. For now, we exist in a universe rich with motion. Galaxies spin, stars burn, planets orbit, life evolves, consciousness emerges. All of it made possible by motion, by the fact that nothing in the universe has ever been still. We are patterns of motion. Our bodies are not static objects, but dynamic processes. Atoms flow in and out, replaced over years. Cells divide and die. Electrical signals race through neurons. Chemical reactions cascade through tissues. What we call life is not a thing, but a process, a temporary configuration of matter that maintains itself through constant change, constant motion. Even our thoughts are motion, neurons firing, ions flowing across membranes, neurotransmitters released and absorbed. Consciousness itself may be nothing more than patterns of motion in the brain, signals propagating through networks of cells, creating the subjective experience of awareness. In this sense, we are the universe becoming aware of its own motion. We are matter that has organized itself in such a way that it can observe, measure, contemplate the forces and trajectories that define existence. We are motion observing motion. Right now, as you finish these words, you are racing through space at hundreds of thousands of miles per hour. You are spinning on a planet, orbiting a star, circling a galaxy, moving through an expanding universe. And you are doing all of this while atoms in your body vibrate, while electrons orbit nuclei, while your neurons fire and your heart beats and your lungs fill with air. Stillness is not just rare, it is impossible. Motion is the only state the universe has ever known. From the Big Bang to the present moment, from the smallest quantum particle to the largest galactic supercluster, everything moves. Everything has always moved. Everything will always move. Perhaps the most remarkable thing is not that we are in motion. It is that in the midst of all this motion, in the chaos of atoms and the vastness of space, patterns emerge. Stars form, planets cool, life begins, consciousness arises. And for a brief moment, in a tiny corner of an expanding cosmos, we exist, we notice, we wonder. In a universe where nothing is still, where motion is the only constant, perhaps the greatest gift is simply this, that we are here to observe it at all.